Welcome, everybody, to another one of our Python seminars. Today, we're going to be talking about, what was that again? The pandas index. Here's the story. Many of you might have some reason to use a tool called pandas, or maybe a tool called numpy. And you might have looked at these tools and said, it seems very easy. I could pick up this API in an afternoon. There's just a bunch of operations. And then you start using the tool, and you're like, why is this so difficult? This seems so impossible for me to understand what these error messages are telling me. What is the core mental model? How does this tool want me to use it? Well, if you forget anything in your life, the one thing you shouldn't forget when you're using pandas is do not forget about the index. I want to share with you in this session the one trick that will make pandas make complete and total sense. The one thing that you just have to remember to make all of your pandas code intuitive and obvious. And that one thing comes down to the idea of the index. Now, we've talked about the index many times before in the advanced workshops, in previous seminars, but I want to share with you a different perspective to really give you a sense for why, of all the things that you can forget, don't forget about the index. As with all of our sessions, this session will be live coded, and so I'll get started by sharing my screen. Behind me, you'll see my screen, and of course, I will hide in the corner here, and let's jump right into this. Let us set a scenario in front of ourselves. Let us suggest that we have some data file. In that data file, we have some information about the network, and it's information that we've generated automatically. It's random data, but it's data that might look somewhat similar to some data that you might have used before, namely information about individual devices, and information about the bytes in, the bytes out, the temperature on the board, and the temperature on the case, the data center that device belongs to, the building that data center belongs to. And it looks like this. It's a CSV file. It's one of the files that we have, and we have questions about it. For example, what is the bisectional capacity of the data center? What's going on with the temperature measurements? Is there something with our passive cooling that's affecting our devices in some fashion? Is there a correlation between one of these signals and the other? Is it the case that the bytes in, bytes out is affecting the temperature on the board or the temperature on the case? What's the relationship between the temperature on the board and the temperature on the case? And how do we look at that on a per data center basis? Now, if we wanted to analyze this data, one of the simplest ways we could analyze this data is using pure Python, nothing beyond what's in the standard library and the built-in types. And you can see here, I'm just printing out the data to the screen. But what if I want to answer a question about the bytes in and the bytes out? What I might do is I might read this data into two Python lists. And when I read this data into two Python lists, I can ask questions. Here's one of the lists, the bytes in data. Here's the other list, the bytes out data. I could ask something like, what was the max bytes in that I see? So this is the maximum bytes in that I happen to see for any of these devices. And clearly, this is probably not an aggregate number because otherwise it would be way bigger than 149. Maybe this is the number that's captured in each interval of time. I could ask a question like, what's the maximum bytes out? It's very good. But what questions would be tricky for me to answer in this formulation? And largely, when you think about the tools that you use, the tools that you choose to use are often motivated by what is made easier or harder for a human being to both write and to understand as written with regards to these different analytical tools. And so, a question that may be a little bit difficult for me to solve here is, well, what was the maximum differential between the bytes in and bytes out? Are there devices that are transmitting way more than they're receiving? And I can solve that, and I can do that with a little bit more code. I need something like a comprehension syntax. And you can see the maximum difference between bytes out and bytes in was 84,000. I'm guessing that's kilobytes. Now, if I wanted to go a little bit further, here I'm just using the built-in list type. And I wanted to use something a little bit more than that. I might think that it might be useful to use a tuple to represent each one of these entities, because if you really think about it, how often is it that you want the bytes in, bytes out value? Usually when you take a look at some of this data, you care about the entities, not the signal measurements on the entities. It's not that you want the maximum differential between bytes in, bytes out. You want the device which happened to have the maximum differential between bytes in and bytes out because you operate in terms of devices. You want to go see what's going on with this device. Is there a reason why this is happening? Can I track this against all of the different work tasks that have been done against this device, the maintenance schedule? And so it's not the individual value you want. You want the value to then drive some information about the entity. And so what you'll do is you'll read in this data as tuples. And you'll compute, you'll pull in the bytes in, bytes out, the temperature and whatnot. And you'll put this into a Python list of tuples. And when you look at these, we get each individual entry. And we can see there's an individual entry for the date when this measurement was taken, the device, the bytes in, the bytes out, and whatnot. And with this, we can do something kind of useful. We could ask for the maximum entity, or rather the entity which happened to have the maximum bytes in or bytes out. And that's a lot more useful than just knowing the number. 149,000 kilobytes or bytes maybe not mean anything, but oh, this is entity CBTJW. Oh, well, maybe I should check to see what's going on with that entity. Well, if we take this a little bit further, we might think that we might use something like a named tuple in order to make our lives interacting with this a little bit more convenient and to make our code a little bit more readable. In other words, instead of having to do key of entity square bracket something, we could write some code like this. What is the max of all of my entries based on the key, where the key is deriving the entity's bytes in or the entity's bytes out, or even the entity's bytes in minus bytes out. And when you look at this, you say, oh, you know what? That's actually kind of useful. Not necessarily because I can do something I couldn't otherwise do, but because I can understand what this line does in a way where the previous line was a little bit too mechanical, perhaps even overly mechanical. I could go further with this. Tuples, great, but why don't I try and read this into a dictionary and see if I can make this even better? So I'll use csv.dictreader and I'll read this in, and you can see I can get the bytes in and the bytes out, the temperature of it and the case. I can turn those into the appropriate integer and floating point values, and the code here looks very similar. What's the maximum across the entities? Looking at just the bytes in. But one of the things that I might find is clumsy to do is to categorize this information. What if I want the maximum entity on a per data center or per building basis? I don't want across all the data centers, across all the buildings. But what was the max bytes in or bytes out value that I saw per building, per data center? And in order to do that, I might need to have some sort of dictionary that classifies these, that groups them. And so my data loading will look identical to before, but now I'll have a subordinate structure, a by day default dictionary, where I'll go through all of the data, I'll figure out what the date is for that data, I'll append it to some structure, and then what I can do is I can say, give me all the data for the second of the month. And here you can see all the data of the second month. I've now grouped it and categorized it. And from that, I can say, for each date, give me the max for that date. And you can see this is a very simple group by, just using a dictionary in order to categorize these, a default dictionary to categorize them, 3 lines of code. And so for the first, we can see what the maximum is. For the second, we can see what the maximum is. And if we wanted to, we could use this key function in order to see what the corresponding entity is. We could have done all of those things. But you can see this starting to get a little bit more mechanical again. We've gone back to this comprehension syntax, and we've gone back to this idea that we can't just express the intentionality directly. We have to express the mechanism by which we accomplish that. We have to express the looping with the comprehension syntax. Now, if I wanted to answer another question, like for a given date, for every entity, what was the difference in the bytes in and the bytes out? You might think I have to do a loop like that. I have to go, on a per date basis, per entity, take the bytes in for that entity and the bytes out and subtract them. But I can actually dig a little bit deeper into the collections module. In the previous example, we used the default dictionary. Here, we could make this a default dictionary not of lists, but of counter objects. And what we could do is we could look at what's happening on the second of the month, and you can see this is a counter object. This is itself a mapping between the entity and the particular value we're looking at. And here you can see we're looking at the bytes in on a per day basis. And these counter objects have a very nice property. I can manipulate them directly. I can subtract them from each other. So I could say, take all of the entries for the second of the month, take all of the entries for the first of the month, and find the difference. And with one line of code that does not expose the mechanics of the looping directly to you, thus cluttering your view and your understanding of what's going on, you can see, oh yeah, this is all the data, all the bytes in data for the second minus all the bytes in data for the first. Or if I wanted to, I could do the first or the second plus the third. And you can see this counter has some intelligence to it. When you add them together, it figures out how to line up the entity entries. So it adds in CBTJW against CBTJW for the 2 dates, BVALI for one date against BVALI for the other date. And if there's a gap, if one of these 2 structures is missing some data, it will fill that in with a 0. That's a very useful property. That makes this code very straightforward, and I can look at it, and sure, it's mechanical, it's code after all. But looking a little bit past the jargon, I can immediately see what somebody was trying to do on these 3 lines of code. And this is what we want for our Python code. This is what makes Python a good tool to use. This is why we choose to use tools like pandas, not necessarily because of performance, but because of the understandability, the readability, and our expressivity of human intentionality. Now, I want to show you something about these collections.counter, because it's a great example for leading us to the idea of alignment. But here I have 3 counters representing 3 days. On day 1, I have A, B, C, D, E, F, and X, Y, Z. On day 2, I have A, B, C, D, E, F, and X, Y, Z. And on day 3, X, Y, Z has gotten decommissioned. It's no longer in the entries. Just to make this very clear, when I do mathematical operations on these counter objects, it will line things up. And so if I do a subtraction, it'll find the value for X, Y, Z in one and the value for X, Y, Z in the other, and it'll line it up and perform the subtraction. If I do an addition, it'll line up the 2 values, and it'll supply a 0 if one of these entries is missing. So between day 2 and 3, where X, Y, Z gets decommissioned, it just assumes the corresponding value for that is 0. Now, one thing about the counter is, typically when we use the counter for things like subtraction, we're assuming that the minimum count is a positive number, 0 or greater. And so you can see, if we were to perform a subtraction, well, the subtraction is just going to remove entries. The counter is assuming that it's counting things, and so these are always natural. And that may not be generalized enough for our purposes, because we can think, for bytes in, bytes out, I think that kind of makes sense, because these are going to be natural numbers. You can't have negative bytes in or bytes out. But for other measurements, it may be the case where negative values are completely appropriate. I mentioned that we want to use pandas not for performance. But why don't we talk about performance? Well, we cannot escape the idea that if we're doing some large-scale data analysis, we need the code to be fast. We just can't escape that. And we can't escape that Python itself, this pure Python code, is not particularly fast. We don't have direct control over memory use, and so things are very large. For example, a tuple of 3 integers can take up to 64 bytes in Python, even though the underlying data is only 24 bytes in size. So even very simple structures in Python have so much overhead that the overhead may be larger than the data itself, meaning we just can't store that much data to perform analysis on. Secondly, we don't control where things are laid out in memory. So if we had a data set, all the data is going to be scattered throughout memory. So to do some operation, we're going to have to jump around, what they call pointer chasing, and that's not going to be as fast as if we had contiguous blocks of memory. Additionally, Python is extremely flexible. Things like the counter show you that you can redefine what it means to add things. Well, the other side of redefining what it means to add things is every time somebody asks you to add 2 things, you have to say, what do you mean by add X and Y? And that dispatch, that determination of what's the behavior that has to be done dynamically, adds some slowness. Whereas you can think for data analysis, you're working with integers, you're working with floats. There's not really a question what it means to add 2 integers or add 2 floats. You can just implement that directly in hardware. This may lead you to the choice of the numpy.ndarray. And so let me load in my bytes in, bytes out data as numpy.ndarrays, and let me also load in my entities as numpy.ndarrays. And when I look at these, I can see I have a 1.5 million bytes in values, 1.5 million bytes out values. And one of the nice things about the ndarray is I can take the bytes in values and do bytes in minus bytes out and align them up. It'll take the first bytes in value and the first bytes out value, subtract them, the first bytes out value and the next bytes out value, and subtract them. And as long as this is meaningful and correct, this is incredibly useful. Before I had to do this in a comprehension syntax, here I can just say bytes in minus bytes out. Kind of like that collections.counter can do this subtraction and addition. And I can perform operations on this. I can say, what is the min or the max of the bytes in, bytes out? Oh, that's the minimum and the maximum value. If I wanted to figure out what the corresponding entity was, I could take this and instead of doing a min or a max, I could do an argmax, which identifies which entry in the array, which entry in the structure happened to have that minimum and that maximum. And it'll say, oh, entry 47. And then I could index another array, the entity array, with this value. And you could see, oh, the maximum bytes out minus bytes in is this device AZPON. Fantastic. That's way better than what I had before. Even though this seems a little bit mechanical, we have to go through these indices. We have to do this argmax. It's still way shorter and way more direct than we had before. However, there should be a voice in the back of your head saying, what if these aren't lined up correctly? what if somebody shuffled one of these? Then the bytes in and bytes out doesn't match up. You can't take the bytes in from one device over here and subtract from it the bytes out from one other device here. You have to make sure that these three separate structures are lined up, and the 0th value for bytes in is the same as the 0th value for bytes out in terms of the entity, as matches the entity in the 0th entry of the entity structure. And when you do that, you might say, managing these three distinct numpy and D arrays is rife with problems, because if somebody accidentally changes the ordering of one of these, they accidentally shuffle them, all of my subsequent data is now completely incorrect, and it'll be very difficult for me to assess that it's incorrect. All it takes somebody to take this bytes out and accidentally do a shuffle or a sort on this, and now all of my resulting data is meaningless. And so what I would love to have is a numpy and D array where I can line up these individual one-dimensional data sets, where I can line up this bytes out value matches this bytes in value matches this entity, and I can have a row where each one of those entities are tied together in some fashion. Thus, I will reach beyond the numpy and D array. And before I reach for pandas, what if I reached for another tool, a very useful tool called xarray? In an xarray, we have a thin, pure Python wrapping layer on top of a numpy and D array. Xarray provides us with a structure called the xarray data array. And what I could do is I could take my bytes in values and my bytes out values, and I could vertically stack them. Now, if you're stopping me here and saying, wait, VStack, is it VStack or HStack? I can't tell my left or right. I can't tell my horizontal from my vertical most of the time. This always throws me for a loop, but just think about this. We have the bytes in values. We have the bytes out values. Instead of being two 1.5 million long structures, I'll make it a 2 by 1.5 million structure. I'll just stack them on top of each other. That way, I put them into the same piece of data, meaning I cannot incidentally or accidentally sort one but not sort the other, and it forces them to be tied together. That could be very useful. Now, of course, I could do a shuffle with an axis or something crazy like that, but generally, the accidental use case, the inadvertent use case, I have precluded. And so this xarray data array is great, but the VStack comes from NumPy. What did the xarray data array really give me? Well, let's just quickly take a look at what this xarray has, and we'll talk about what this xarray gives you. You can see I've now stacked these values on top of each other, and then I can do a subtract operation to subtract the 0th row from the first row, and here are my bytes in, bytes out, and I could even say do a max on this, or I could say it's 130, 480, or I could say do an index max, tell me which index happens to have this. Oh, and there's no coordinates. We'll talk about what that is in a moment. So I could do a arg max here. Now, and you can see the 1.2 millionth column is the column where I happen to have this maximum value. Now, you saw that error about missing coordinates, the missing dimension. One of the things that xarray gives me is the ability to name these axes. So instead of having a 2 by 1.5 million structure, that 2 measurements and 1.5 million entries for those measurements, or is that 1.5 million entities and 1.5 million measurements and 2 entities? Probably it's the former, but it would be nice to have some labeling to better tie this data together. Xarray gives you the ability to name the dimensions. And so the data is the same, but now I have some indication that this axis here, the stacking, represents measurement 1 and measurement 2, and this axis here represents each individual entry, or in this case, each individual entry rather than each individual entity, because we had these as time series data. And then I could do something like this. Compute the mean on axis 1. So that means compute the mean across each entry. So that means give me the mean value for the bytes in measurement and the bytes out measurement. Axis equals 1, that's a little bit hard to read. Wouldn't it be nicer if I could specify the dimension by name? And here, we'll fix this name here. Give me the mean across all entries. So whenever you do these reduction operations in NumPy and xarray and pandas, you should always think of the argument here as that's the axis that you remove. That's the axis you eliminate. So compute the mean, but no longer distinguish from entry to entry. So retain the distinction between measurement to measurement. Well, that's the mean for one measurement, the mean for the other measurement. Or compute the mean, eliminating the entry distinction, but eliminating the measurement distinction, but keeping the entry distinction. So this is the mean of bytes in against bytes out. And a subtract on this dimension as well would be the subtraction of each entry against each entry, preserving the entry distinction, but eliminating the measurement distinction. And I can do further things. I can compute the max across each one of these entries. And so here is the maximum value for the mean, eliminating the distinction between the two measurements. So the mean bytes in against bytes out for each individual entry. And here we go. This is starting to get kind of useful. But there's one thing that you might spot on the screen: dimensions without coordinates. What does that mean? Well, another thing I could add to this X-ray data array, a coordinate system. Instead of saying, oh, here's what my dimensions are. This means the measurement. This means the entity. What I'll say is, this means the measurement, and this one, the tick label, is bytes in. This one, the tick label, is bytes out. And this means the entity, and I'll put a coordinate system on it, and the coordinate system I'll put on it is the name of the entity. Hold on a second. Now this becomes really useful, because if I look at the data, you can see I have two measurements: all my bytes in data, all my bytes out data. And for each one of these, I say, oh, this is the data for AP LGT. This is the data for CIDFA. This is the data for CEMUQ. Now, bear in mind, what I'm going to do here could be done completely in NumPy, could even be done in pure Python. But I want you to see how we've improved the readability, the understandability, and the directness of expressing your intentionality. In other words, I could say select the bytes in measurement. Selecting the bytes in measurement, tell me what the maximum position of the value is. So at index 387719, we have the maximum value. Or tell me the coordinate entry for that. AAFZZ is the maximum for the bytes, is the maximum entity for this bytes in. Here, the code is shorter than what we had before, and it is very direct. It tells you explicitly, select this measurement and give me the corresponding coordinate entry across the remaining axis for this maximization. This should lead us directly to the tool that we actually want to use. If you look at these data sets, you'll notice that they're all one-dimensional data sets. And my goal here is to take those one-dimensional data sets and to tie them together in some fashion. To say this entry in the one-dimensional data set, this entry in the one-dimensional data set, and this entry in this one-dimensional data set all correspond to the same underlying entity. So I can do mins, I can do maxes, I can do operations on that, and go back to what the entity was. I can use this data in order to drive lookups into other parts of the data, in order to drive other lookups, in order to take this enormous data set and to narrow it down to the actual data I care about. Well, let's take a look at what a pandas.DataFrame really is. We'll go back to our data. Now our data will be in CSV format, and we'll read it in using read CSV. And you might have stopped me at the very beginning of this presentation and said, are you using CSV.reader? Of course you use pandas. Pandas has read CSV. It does everything you could ever ask from a CSV reader. Largely, read CSV is an enormous convenience, but it is not the motivation for why we choose to use pandas. And it is not the motivation for why we choose to use pandas because largely the data type that we get out, the structure, and the features of the structure, namely these ideas of alignment and tying this data together, that's what pandas gives us. That read CSV, it's just a convenience layer. We could write our own read CSV using the standard library. It is the structure that's useful. It's not the reading operation. It's not the data loading operation. Let me show you what I mean. If you look at this structure, what you can see is each row of that CSV data has been tied together. And it's been tied together saying, oh, this date, this entity, this bytes in value, this bytes out value, this temperature on the board, and this temperature on the case all correspond to one row, all correspond to this entity as of this date. Additionally, vertically or horizontally, I can never remember which, we can say all of these pieces of data in this one-dimensional structure, all of these pieces of data in this one-dimensional structure, all of these pieces of data in this one-dimensional structure have a label. This is the bytes in, the bytes out. And that's not too different than our idea of the coordinates on the named dimension. I can use this in pandas and I can say, oh, give me the column for bytes in. Here's all my bytes in values. And if I look at this column really closely, I'll see, oh, hold on a second. Under the covers, it's just the same old numpy.ndarray that I was working on before. I've just added some labeling to it. I can say, give me the bytes in column minus the bytes out column, and it subtracts all of these, just like it did for the numpy.ndarray, but it retains some labeling, and that labeling seems to be the row number. I could do my maximization here, and I could subtract these, find the index max, find the corresponding row, go into the entity and see if the right entity matches my bytes in minus bytes out, BVALI, I think that's the right one. But there's something missing here. If I rewind to the original data, what you can see is this far left column that doesn't have a label on it is what we call the index. This is how we're tying together every row. Notice this is a very simplistic index. It's just a number saying, oh, row 0, row 1, row 2, row 3. If someone were to ask you, tell me about the device which happened to have the highest difference between the board temperature and the case temperature, would they want you to say, oh, device 43? Or would they want you to list that device in terms of, oh, device CB-TJW on the 4th of the month at 11 o'clock? Which is more useful in practice? Obviously, the latter. This is what happens when we use pandas just for the conveniences, but we forget about the index. And I'm going to tell you something, and you need to remember it. Hopefully, you have an opportunity to take a break after a long year. Hopefully, you might even have an opportunity to travel. When you get to the airport, you're going to think to yourself, did I turn off the stove? Did I tell the post office to stop the mail? Did I make sure to leave enough dog food with the neighbor who's watching my pets? If you forget all of those three things, no big deal. Forget your airline ticket, they'll look it up at the counter. Forget your passport, no big deal. As long as you don't forget about the index. The index in pandas is the most important thing, and this here is what we would say a very limited use of pandas because we are not using that index to tie this data together. Let me show you how we should be interacting with this data. Here is our data frame. I've done one small additional thing. I've parsed the dates, and I'm going to take one more step. I'm going to set the index. I'm going to say this data is tied together not just by what row number, but I'm going to put a label on that row. I'm going to say this row corresponds to some date, the 1st of the month, at 46 minutes past midnight for this data center, for this building, for this particular entity. And just to make it easier for me to manipulate this data later, for me to be able to look at it nicer, I'm going to sort that. So I'm going to say sort them all by time, and then by data center, then by building, then by entity. That'll help me if I want to look at data centers, all the elements for one data center, all the elements for one building, all at once. Once I do that, I can now use this .lock accessor to intelligently query the data based on that labeling. I can say, give me all the data from 9 a.m. to 10 a.m. That is a very useful thing to do. Computationally, from 9 a.m. to 10 a.m. just means from row 53 to row 64. But to a human being, row 53, row 64 doesn't mean anything. To a human being, 9 a.m. to 10 a.m. means a lot. Additionally, I can use some jargon, some mechanism from pandas, index slice, and I can say, give me this data and look at it across multiple layers of this hierarchical index. You can think for each layer of this index, the date, the data center, the building, the entity, well, the entity kind of rolls up to the building rolls up to the data center, and we have one of these entries per date. Well, I can say, give me all the entries from 9 o'clock to 10 o'clock for one particular data center. Quite useful. And I can say, give me all the entries from 9 o'clock to 10 o'clock for every data center, for every building, but for these two entities. Now, of course, entities might be unique to particular data centers or buildings, but you could think that there may be some additional identifier, like the role of the device, what kind of switch it is, what kind of router it is, what kind of service it provides, where you might say, give it to me for all of these services across each one of these layers. And that's incredibly useful because when somebody asks you a question about this data, they're going to ask it in human terms. And if you can write your analytical code in human terms, modulo a little bit of pandas jargon, modulo a little bit of mechanism that any computational tool will ask you to employ, you can write code where you can answer extremely complicated questions, but the complexity of phrasing the question as a human being will actually largely match the complexity of phrasing it computationally in pandas. In other words, pandas isn't really about solving the trivial, easy problems, because you could solve that in pure Python or even with NumPy, and you can kind of make your way to solving problems. Pandas is about finding analytical problems which are difficult for you to phrase in English, but they are incredibly useful, and where it's difficult to phrase in English, but it's possible to phrase it in pandas, versus, as we'll see, when we do these things in pure Python or NumPy, difficult to phrase in English, and it is close to impossible to make heads or tails of the enormous amount of code that's required to phrase that using all of these nested comprehensions and all of these subordinate dictionaries and all of these other tricks that you might need in order to do Python. Let me shake this example a little bit further, because there's something that you might have noticed about this data. There is a relationship between some of the columns of this data. The first thing that I did when I looked at this data is I said, you know what, this index is not particularly interesting. I'm not going to forget about the index. The first thing I'm going to do is going to set my index. I'm going to associate all of this data together. But the data is now just a bytes in, bytes out, and the temperature of the board and the case. You know what? That data is interrelated as well, because the bytes in, bytes out are in the same unit, and the temperature of the board and the temperature of the case are in the same unit, degrees Celsius, centigrade, Kelvin, Fahrenheit, whatever the case may be. Bytes, kilobytes, gigabytes, terabytes, whatever the case may be. And it might be useful to look at the bytes level data all together, the temperature level data all together. So what I'm going to do is I'm going to use a little bit of pandas jargon, and definitely the pandas jargon, it's worth learning. There's a little bit to it, but I'm going to add another layer of organization here, and I'm going to say, give me the ability to look at the bytes data, including the in and the out, or the temperature data, including the board and the case temperature. And when I go down to my query, you can see I can start expressing some very complex things. I can say, give me the data from 9 o'clock to 10 o'clock for these two entities, and give me all the bytes traffic related data. Probably should call that traffic instead of bytes. But you can see it gave me the in and the out. And I could even do something like sum this, eliminating the distinction between the columns. That's how you should interpret the axis. And so here, this is the total throughput, bytes in plus bytes out. Oh, that's kind of useful. I could even do the same thing for the temperature and say, oh, compute a mean, and compute a mean, eliminating the distinction between the columns. And so that is the mean temperature between the case and the board for this particular set of devices for these particular dates. And so you can see I have this multi-index on my columns. Now, I don't want to go into the mechanics of the multi-index because we've talked about this before, and we can talk about this in a future session. What I want to motivate for you is, why even bother? What is pandas all about? And you know what? I've forgotten my point. As long as I didn't forget about the index, I'll be fine. Let me show you something else I could do. Let's say that I added some additional information to this data. Maybe I add packet level information. I got bytes in, bytes out. Maybe I put in the number of packets that I have. And I'll synthesize that with some dummy data. For now, it's all dummy data in the end. What I could do is I could use that same index slice trick. And I could say, give me the data and slice into it, grabbing all the data from 9 o'clock to 10 o'clock, all of the entities in this particular list of entities, and give me all the in-level data, the bytes in and the packets in, or give me all the out-level data, the bytes out and the packets out. And maybe I might use that in some fashion. I might compare. This could be bytes in against packets, maybe isn't that useful, but think about something like your netstat output, your failure versus success versus retransmits and whatnot. That is definitely comparable. If you had packets, failure, succeed, retransmit, or something of that nature, and you said, oh, give me the average here, give me the difference here, very useful. And you can see what we're using this index for is to subset this data. If we think about a pandas data frame, we can think about a pandas data frame in terms of three things. When we think about a numpy.ndarray, we're thinking about some block of multi-dimensional data. Pandas data frame has that and more. It's called the .data, and that's the data in the data frame. When we think about a data frame, however, we're thinking about that data with some labeling for each one of the rows. That's the index. You can see each one of these are the entries where we labeled the rows. And we use that in order to answer our questions. It is a human-readable piece of metadata that drives our analysis. Additionally, there is another thing. That itself is a type of index. I usually call it a minor axis or a minor index. There is the labeling of the columns. What you can think is pandas is all about labeled data. One-dimensional data structures, time series type things, with the labeling on one axis and the labeling on the other axis. And we saw that exactly with the X-ray data array, right? We had two axes, one that was the measurement that we were dealing with and one that was the entity we were dealing with or the entry that we were dealing with. We labeled them. That's all pandas is, just a labeling of two axes for data that might not quite be two-dimensional, because you can think temperature and packets and bytes, you can't really compare them against each other. It's not like some two-dimensional structure that you can arbitrarily rotate. It is more like one-dimensional data structures that you've just lined up and then labeled. There's one additional useful thing. When we looked at NumPy, we saw how things align. You know, when you do subtraction, you just express subtract. You don't express the looping like you would have to do in pure Python with the list. Well, NumPy, pandas, the counter, they all support some notion of alignment of operations. And I want to share with you what that means. If I had two values, x and y, and I took the sum of these two values, and x is 1 and y is 1, well, the answer is going to be 3. I'm not that good at math, but I'm pretty sure that's the right answer. If I took x and y, and it was 1 plus 2j and 3 plus 4j, well, I still kind of remember how these work from high school math. These are complex numbers, and you add the real components separate from the imaginary component. And so I guess you could say there's some kind of alignment here, because I took the 1 and the 3 and I added those up, and I took the 2 and the 4 and I added those up, and I didn't cross these. I didn't take the 1 to the 4 and the 2 to the 3. That's what I might do for multiplication. At least for addition, I always line them up. I always add real against real, imaginary against imaginary. Otherwise, it's not meaningful. If these were two counter objects, which counted these letters, A appears 4 times, B appears twice, C appears once in X, A appears 5 times, B appears once, D appears once in the other, and I add them up, counter objects add up in aligned fashion. I add the A's against the A's, the B's against the B's, the C's against there's no C's in the other, so I supplement with the 0, the D's against the D's. No D in one of them, I supplement a 0. What you can think is, there's some logic behind the scenes to match things up when you add them up. Now, when we talked about the numpy and DArray, we said this was one of the humongous risk cases that we might have. Because if somebody had shuffled one of these structures, they wouldn't be aligned anymore, and the result would be garbage. You'd be taking one device and the information from one device over here, and another device from the information over this device, and adding and subtracting them where you're not adding like to like. And you wouldn't be able to get any reasonable result. Well, it is the alignment of those numpy and DArray subject to you making sure that they're lined up that makes this useful and powerful. And if you look at that example again, and we take two numpy and DArrays from 0 to 1, or from 0 to 2 and 0 to 2, we can see, the 0 adds to the 0, the 1 adds to the 1, the 2 adds to the 2, they line up. If we were to reshape these such that y was two-dimensional, you can see that NumPy adds a little bit more to the story, the rules of broadcasting. NumPy structures align in a broadcasted fashion. If one of these structures is two-dimensional and the other one is one-dimensional, it's actually going to add x to the first layer of y and then to the second layer of y. So you can see that 0, 1, 2 was added to the 0, 1, 2 and then to the 3, 4, 5. It's adding a little bit of additional logic to figure out how to take dissimilarly shaped things and join them together to add them up. Join them together kind of sounds like SQL. Kind of sounds like what I need to do if I have multiple data sets and they're identified by the same underlying identifiers, and I want to connect them in some fashion to a meaningful analysis. Basically what the pandas is. If I take two pandas series, and one of them contains A and B, and the one contains B and C, and I add them up, you can see the A's add up, the B's add up, and the C's add up. But unlike the counter, which assumes that if something's missing from one side, that's a 0, because counter is counting things. So if you haven't seen it before, that's a count of 0. Pandas says, I'm not quite sure in general what you mean, so I'm going to nan fill this. I'm going to say if data is missing from one side or the other, consider it missing and make this a nan value. And what you can see when you do this operation is the common entries in both of them persist, and the uncommon entries, the ones that only exist on one of the two structures, are nan filled. The B against the B adds, but the A and the C don't. And if I were to change this very slightly to add in an A entry, and note, I add the A entry here at the end, and it will show up here at the end. It doesn't matter because pandas is lining them up on the labels, not on the positions. So even though the A is at the beginning here and the A is at the end here, it still figures out how to line them up. 10 plus 1 equals 11. If I were to take this into a pandas data frame, and X has columns A and B and rows X and Y has columns B and C and rows X and Y, you can see that alignment happens on both axes. I match up A, B against B, C. Okay, there's nothing in the A and there's nothing in the C because they are dissimilar. The only thing in common is the B. There's X and Y and Z. I guess one of them doesn't have an X and the other one doesn't have a Z, so the Y is the only thing that's remaining. And you can see the little box in the middle where there was the only overlap. In general, what pandas does when you take two structures is it figures out how do I line these up to make this operation make sense, preserving the labeling of the rows and the columns, and if there's something missing, I presume that that's a nan and I nan fill it. If, and this is the hardest part about pandas, if you have dissimilarly shaped things, a series, which is just one data signal, one-dimensional thing, and a data frame, which is multiple one-dimensional things, the rows of the series line up against the columns of the data frame. And so here you can see the A on X and the B on X added to this A here and this A here, this A here and this A here. So you can think of the pandas data frame against the series kind of like a mix of the broadcasting rules for NumPy and the collections.counter. And you might look at this and say, I'm not sure why that's useful, but we'll take a look at why this might be useful in just a moment. Let's say that we have our data and we've structured the data just like we had it before. And as part of our analysis, we want to do something a little bit smarter. For whatever reason, we don't really want to count the bytes in, bytes out, or the temperature measurements identically across all. We don't want to count those identically because, for example, we're doing some analysis that privileges the packets in or the packets out, or some analysis that privileges the bytes in or the bytes out. And so what we want to do is we want to say, I pay way more for egress traffic than ingress traffic. Maybe what I want to do is I want to see what's the total throughput here, the sum of the in and the out, but we'll count the ingress more than we count the egress. We'll count the egress more than we count the ingress. What I'll do is I'll create a series that is identically labeled to this data frame. The rows of the series are bytes in, bytes out, packets in, packets out, and the columns of the data frame are bytes in, bytes out, packets in, packets out. And let's take a look at our data frame and our structure here. And what we can do is we can multiply these together. And when we multiply these together, it will line them up. It'll line the bytes in and the packets in against the column bytes in and packets in, the bytes out and the packets out against those columns. And because I didn't specify what to do with the temperature measurements here, it will nan fill those temperature measurements. Oh, so this could be a way for me to say, oh, across every piece of data factored in this particular way. Or what if one of my data centers was under construction, and as a consequence, for my analysis, the temperature measurements or the bytes in, bytes out, I want to discount those in a further way. I pay more for egress or ingress, but for particular locations, I might pay even more. Maybe there's a regulatory concern. Maybe there's some sort of just, accessibility location-wise, or maybe some sort of power requirement, whatever the case may be. I want to factor these not only by which measurement it is, but also by which data center. I could even do that. If I take a look at my information, you can see for WQN and HIB, I have different bytes in and bytes out. I have different factors for the bytes in and the bytes out. And what I could do is I could take my data. I could subset it to all the data from 9 o'clock to 10 o'clock for these two particular devices, which gives me only rows, bytes in, bytes out, packets in, packets out for those times for those entities. And because that lines up with my data frame here that factors things, I can just multiply times a factor and it will scale everything automatically for me. What you can think is this index alignment is our way to take these similarly shaped structures and to, in a meaningful way, express addition, subtraction, multiplication, any sort of operation, saying line these up, but line these up in a complex way across both axes. To, for example, automatically add factoring factors, automatically add up dissimilarly shaped data, where one might be longer than the other, one might be wider than the other, but to find what matches up. And what I could also do is compute the matrix multiplication, the matrix product. And here it's not going to be aligned, but what I want to do is I'm going to have to transpose one of these probably just to line it up. I could even do the sum at the same time. Here you can see I've summed, and this is kind of meaningless, bytes versus packets, but I guess if this were, success versus failure, and I factor them in some fashion, here you can see I even did a multiply sum, all in one operation, all performed very, very, very much within that NumPy restricted computation domain, and thus high performance on these underlying contiguous devirtualized machine-typed, small data. This is the power of pandas. And so, as we wrap up this presentation, I want to remind you of something. Just lost my train of thought. What was I saying? Don't forget about the index. Of all the things that you might forget about when you use pandas, like, is it set axis or rename? Is it reindex or set index? Is it stack or unstack? Is it pivot or pivot table? Those things you can look up. Those things the documentation will tell you what it is. For melt, what are the arguments? Is it value underscore name or val underscore name? Some of you probably knew the answer until I asked that question, and then suddenly you're asking yourself, well, hold on a second, I can't remember now. Which one is it? As long as you remember about the index, your experience with pandas will be a good one. If you forget about the index, pandas will always be this very simplistic but confusing tool to you where it's never doing what you want and constantly giving you these weird error messages that you can't make heads or tails of. All of the enormous jargon and details of the API are things that you need in order to use pandas effectively, but everything complex about pandas comes down to use of the index and index alignment. All of the API maybe can't fit into one person's head, but you don't need to as long as you understand the index and you see the power of this idea. We have done other sessions which we will share with you about some of the mechanics of the index, but I want to show you in the last example we have just the power of what we can do and express. And I want to answer a very complex problem using some pandas jargon. There's going to be a lot of jargon here, but to show you how with index and index alignment and having labeled this data, I can use that in order to accomplish a very useful and very complex goal where the code is still within the jargon of pandas. It's still somewhat mechanical, but it is far more expressive of a human intentionality than if I were to do this in pure Python with a bunch of loops and you'd be like, this is the 15th for loop in a row. What the heck does this even mean? Let's take a look. I am going to read in my data from a pickle file now. I'm going to set my index, the date, the data center, the building, and the entity, and I'm going to do that multi-indexing on the columns. I'm going to sort it. And so we're going to look at the data, and the original data is going to look like just like we saw before. It's a little bit more data. We now have the original 1.5 million rows. And remember, I can do things like look at just the bytes information and sum it across the column. So this is the maximum throughput per each entry. I can even say, take that maximum throughput, compute the mean of that, compute the standard deviation of that, find all of the entries which are greater than 1/2 beyond the standard deviation. Because think about it, bytes data and temperature data, maybe it's the case that something is going wrong with the failure rate in my data. And I have some assumption that maybe devices are overheating when their traffic hits a certain amount. Maybe the fan's not coming on appropriately, but whatever the case is, there's some relationship between the temperature of the device and between how much traffic it's seeing. And I want to really understand what's going on in the data center. So I want to very narrowly reduce this data set, some representative devices that I can then go manually physically check. So I don't care about the values themselves. I care about what the values point me in the direction of seeing and point me in the direction of investigating. So what I'm going to do is the following. I'm going to start with, and we'll go down here, and I'll show you how we can step through a very complex example. I'm going to start with my data, and I'm going to use index slice to only look at one data center, because maybe as part of my analysis, I've identified that the only problems are in WQN, or at least it's representative. Maybe I live nearby WQN, so I can drive out and I can go and see what's going on there. I've limited my data to that. Now, what I want to do is I want to take that data and look at just the bytes column. And I want to do that sum to just figure out what the total throughput is, because I have some assumption that, it's related to the total activity that the interface is having. So I'll sum in the bytes in and bytes out. Now, I want to do a grouped operation on this. I want to say, you know what? These are individual measurements on individual times that I've pulled from my time series database. And really, I expect that the problem has something to do on a day-by-day or hour-by-hour basis. It's not on an individual measurement basis. It's not like the device just one moment in time it's going crazy. There's some persistent issue that I can see on the fidelity of a couple of hours. So I'll group this by the day and I'll sum them up. And so here you can see for each individual day, I have the total of the bytes and bytes out throughput. Now, notice that this grouping operation changed my index. So now my index indicates the labeling of the data. And since I wanted to group it by day, my index is each day. Now, I'll do one little piece of jargon here, and there's going to be some jargon in this exercise. I'll turn this into a data frame, and I'll call this column the throughput, or maybe the daily throughput. Here you can see for each day, I have my throughput value. Now, what am I going to do with that? Well, I'm going to take this to the next step. And I want to identify when something is going wrong by looking at sequential days in my data set. Because I don't think the problem is just one moment in time, or even 1 hour, or even a 6-hour block, or even a day. I think there's some problem that's extending over multiple days, maybe related to some maintenance issue, maybe it's related to fires forcing me to close the windows of a passively cooled data center, and so everything starts heating up, whatever the case may be. And so I'm going to do something kind of crazy. I'm going to take my throughput, and I'm going to find all the places where that throughput is greater than 1/2 of a standard deviation above the mean. And I'm going to generate a true-false set of values for this. And you can see here, I've created a new structure with the same indexing as the original input, which was just the date and the value, and just true-false. Was this greater than the mean plus 1/2 of the standard deviation? Now, here's where I'm going to do something kind of tricky. And this is a pro tip for pandas. Whenever you want to find consecutive days of something, what you do is you take this signal that indicates whether the flag was set. Was this of concern or not? False, not of concern, true, of concern. And you're going to negate it. And now, what it tells you is true, not of concern, false, of concern. But because true and false are equal to 0 and 1 in Python, if we compute the cumulative sum, then all the false values add up to 0. All the true values add up to 1. And so what we see is we see some counting here. 1, 2, 2, 2, 2, 3, 3, 3, 4, 5, 6, 7, all the way up to 615. And you can see some of these values must be repeated because the length is 834, but the maximum value is 615. Well, because false meant of concern and true meant not of concern, what you've actually computed with these values are where it switches from a string of concern to not of concern. Because if for 3 consecutive days it was false, 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 and you did the cumulative sum, then whatever the value was before would be plus 0, plus 0, plus 0, plus 0. So now if you take a look at this value and you group by this value, it can tell you how many consecutive entries you had. It's a pro tip. And so what I'll do is I'll take this structure and I'll group it by the values. And I'll transform this, retaining the index, so I still have those dates, and I'll see how big these are. And now I have a structure that looks like that index date structure, but now I know how big each one of those consecutive windows is. So I can identify, was there a consecutive window more than 3? 3 consecutive days where the throughput was higher than the standard deviation, which is leading me in the direction of, when the throughput goes more than a 1/2 standard deviation above the mean, something goes flaky with my firmware or my operating system that's causing this to overheat, that causes some issue with the temperature on the board in the case. I will then take this data and I will subset it. So I'll look at all the dates where this is the max. And now we can see, oh, there were 5 days in a row from the 30th of July to the 3rd of August when this signal was high, when the throughput averaged in the way that I've looked at this was greater than 1/2 over the standard deviation. Oh, okay, that's useful. Then what I'll do is I'll go back to the original data and I will take this information that I have, these dates, and I'll just take the index. I don't care that it's 5 days in a row. I care which days. So I'll take the dates, the index of this, the 30th, the 31st, and so forth and so on. And I'll take the index of the original data, round it in a similar fashion to the date, and I'll see, well, is this date in this index? And what that will do is allow me to get all the way back to the original data. So here's the original data, subject to the filtering of WCAN only and the longest sequence of consecutive days where the throughput was greater than 1/2 standard deviation above the mean. Now, here I'm only looking at one data center with multiple buildings. Maybe the problem is related to the buildings, maybe the placement of the buildings, maybe some common service, maybe some common heating or cooling service, or some maintenance schedule between the buildings. What I'll do is I'll take the data and I'll go back to my temperatures, my case temperature. And what I'm going to do is I'm going to group that by 6 hours. Look at every 6-hour window, non-overlapping. And I'll further group this by the building. I'll find the mean on a per building basis, and I'll actually show you. This gives you, and here, this is the mean on a per building basis. But, this is, I'll show you what the max of that mean is. Find the mean on a per building basis, but I don't want the value. I don't actually care about the values. I care about the entities. So here, what you can see is I took the data, I looked at the temperature values, the case temperature values, and what I've computed is the mean. Well, what I want from that is not the max. I want the index max. When you start using the index in pandas, what you end up doing is looking for the index in order to drive lookups into the data. So what I actually want here, tell you what this looks like, here is which building on a 6-hour window saw the greatest mean temperature for all of the days within my largest consecutive window for WQN. So now this is actually kind of interesting because it looks like WQN1 has the problem, but in one of these 6-hour windows, WQN2 has the problem. That's very interesting. Maybe there's something, maybe that's when somebody changes shifts. That's when they go from working in WQN1 to WQN2, and maybe that points to a reason why this problem is happening. Well, I want to further dive into the data. And so what I'll do is I'll group this again by the same grouping as before, 6-hour windows, and by the building. And I will filter this data. And I will filter this data to find the places where the window, I'll go back to the original data and I'll find the place in the original data where I'm only looking at the particular building that was flagged as being the greatest mean temperature for that window. So I've gone all the way back to the data again. But now I'm looking at the data subject to a very complex but human understandable predicate. Only WQN for the longest stretch of consecutive days, only for the buildings where those buildings happen to have the highest mean temperature in a 6-hour non-overlapping window. And that might give me some information about the entities I need to go look at and to see maybe there's a maintenance schedule that's touching those entities in that particular order, and I'll see that from the data. And so now I think I'm ready to look at the data, look at the entities themselves. So what I'm going to do is I'll go back to the temperature measure. I'll look at just the board and the case temperature. And you know what? I'm curious about what's happening on a 1-hour basis, so I'll group this for each hour. And for each hour, what I'm going to do something a little bit complex. I'll do is I'll take this on a per entity basis. I will filter those entities to the entities where the case temperature's minimum value is greater than 5% over the board temperature's minimum value. I'll figure out which entities I'm talking about, and I'll put them into a Python set. And as a consequence, I end up with this. This is an incredibly sophisticated query that I've accomplished in 25 lines of code that is full of the pandas jargon, but is far shorter, far more direct, far more meaningful and understandable than how you'd express this in pure Python. Here is, for all the devices in WQN, for the longest stretch of consecutive days, for the buildings where they happen to have the highest mean temperature over a 6-hour window, all of the devices in those buildings, in that data center, on those days, where the coldest the case ever got was 5% hotter than the hottest the board ever got. And these are the devices I probably want to look at and try and figure out what is going on with BB, RTW, AAFZZ, and AATFL. This is what you get when you use pandas to the fullest. You get a lot of jargon, you get a little bit more mechanism than you might be used to, but you get the ability to do incredibly sophisticated, complex queries that somebody can actually step through and understand in a way that would be impossible in pure Python and with NumPy, because you have that index that ties the data together in this fashion. And you see that you're constantly look for something and then laterally go back to the original data and subset to that. Then go another subsetting, and then go another subsetting until you see exactly what you want. Problem with large data is it is very difficult to summarize it meaningfully. This is what pandas gives you. And so, of all the things that we've talked about in all of these sessions, many of them have been useful if you're doing pure Python. Many of them have been useful if you're using pandas or matplotlib or NumPy. But if it's the case that you're using pandas, forget whether it's capital P pandas or lowercase p pandas. I get that wrong all the time. Forget whether it's panda or pandas with the S. Forget when you're importing scikit-learn, if it's scikit-learn or sklearn. Forget all of the keyword arguments and all the different things you can do with a group by or a stack and an unstack. The one thing you should never forget about and you should use to the fullest extent possible because it's the reason you're using pandas in the first place, don't forget about the index. But with that, thank you all for joining us. It has been an absolute pleasure having this opportunity to present to all of you. I hope that this session, as well as some supplementary material that we will share with you about some of the mechanics and the rules and the details of the pandas index, will be helpful. But with that said, I'm James Powell, and there's one more thing that I wanted to mention. I talked about index alignment, I talked about numpy, I talked about xarray. Oh, the index! Let's make sure we don't forget about it. Thanks everybody for joining us, and I'll see you next year.